All right, Sebastian Raschka. He wears many hats. Lead AI Educator at Grid.ai. Assistant Professor of Statistics at the University of Wisconsin-Madison. And a recent author. He's written other books, but the newest book is called Machine Learning with PyTorch and Scikit-Learn, which coincidentally is the reason we actually ended up doing this podcast. I'm not sure how much we're going to talk about the book, but I will link to the book in the episode notes, so make sure you check the episode notes. So Sebastian, welcome to the Data Exchange podcast.
Yeah, hi Ben. Thanks for having me here. It's a pleasure. I've been a long time fan of your podcast, so finally I'm here, and I'm super excited to chat about anything like machine learning, my book, deep learning, AI, whatever, whatever you feel like is interesting.
So first question before we go into other things is you mostly work in deep learning. So what the heck are you doing in a stats department?
Oof. That's the tricky one. Yeah, so one thing led to another. So my PhD was actually in computational biology, where I solved problems related to, let's say, small molecule drug discovery, which is essentially like a pattern recognition type of problem. And yeah, I joined the stats department, and I think the reason why they wanted me there is that machine learning and deep learning is a very popular topic, and students are really excited to learn about it because, yeah, the job market, just the exciting problems you can solve with it. There are so many reasons why people want to learn about machine learning and deep learning. And there was a gap in our department where no one was teaching that stuff. So yeah, I joined the department, and I created two courses. One is Introduction to Machine Learning and Statistical Pattern Classification, and the other one is Deep Learning and Generative Modeling. And yeah, I mean, that's what I'm excited about. That's what students are excited about. And also, just to tell you one little thing, actually, my introduction to machine learning was also through statistics. I mean, not quite, but I started with R and statistics, and then I took this class.
So this is Hasty and Subbarani's book?
Not quite. This came later. Yeah. So my introduction to this topic was the class was called Introduction to Statistical Pattern Classification, and there was the book just called Pattern Classification, but it was like the let's say statistics take on machine learning, like with Bayesian methods and so forth. So that's how I got introduced to the topic. Nowadays, I don't really do anything with, let's say, Bayesian statistics anymore or Bayesian methods. It's mostly discriminative models in deep learning. But yeah, that was like my long time ago introduction to the field. So maybe that's also why I ended up in this department.
The youngsters in the audience, before the deep learning renaissance in 2012, 2011, the Bayesians had a good run there. You know, with their variational methods and stuff. I mean, if you go to like the top machine learning conferences back in the day, the Bayesians ruled the roost.
Yeah, I think also that was about the time where like latent Dirichlet allocation and these types of methods were super popular. I remember.
And the variational base. Like,
I was like a small, like maybe undergrad student back then. So I just heard about these methods. But yeah, nowadays, I don't think anyone is using latent Dirichlet allocation that much anymore. But yeah, it was like the thing back then. I remember, yeah.
What? So right now, if you go to a typical top stats department, is there someone like you there now? A designated deep learning, machine learning person?
I don't think so. I think I mean, yeah, we have a lot of people focusing on theory. Actually, our department chair, he's really interested in, let's say, this topic, but let's say more from a theoretical perspective. So I would say, I wouldn't say it's good or bad, it's just how it is, but I think I'm a little bit unique in the department that I'm more applied. So I would say, I mean, I know some math, but I'm not really good at math. It's not my strength. So I like technology, to be honest. I like tinkering with things. I like coding and this type of stuff. And I think in that case, why I fit into the department was like really that most of the people are doing theory research, which is very important. But then students, let's say when they want to get a master degree and then, job, want to go into industry, you also need to yeah, let's say apply things, right?
Yes.
I would say I'm like a little complementary person in the department, where other people teach theory. I teach the students also how to do things in practice.
So right now it seems like just judging from your Twitter feed and your website, education is a big part of what you do. I mean, training people how to become proficient in some of these modern techniques, right?
Mhm. Yeah, I really like that. It's like a fun thing. It's like when I was back when I was a student, I was writing my blog posts. I think it started like in 2012, and then my first book in 2015. Actually, I had a small book on heat maps in R that was, I think, also 2012, 13. But I wouldn't call that a real book. It's more like a booklet. My real book was, or the first real book was Python machine learning in 2015, and I really enjoyed that process of thinking about how to present a topic, how to talk through this topic, and also how to like organize things, like in which order do you explain things, and
have and come up with like working good code for people to take and modify and run with, right?
Yeah, and I like, honestly, I like really talking about this. It's like people read these things, or I also have some YouTube videos when they watch that and I get feedback about it. It's somehow very, it gives me pleasure in a way, like hearing that people find it useful and chatting about that. And then also, yourself, you learn a lot from that. I mean, there are always people who in a specific area know more than you do, and then you get this very expert feedback from someone who knows a little bit more, and it pushes you further, like increases your knowledge in a way that you wouldn't otherwise accumulate this knowledge, because it's really like very targeted expert level feedback. And at the same time, I feel like also the process of organizing knowledge, of writing it down, or even, let's say, designing a lecture, that's also where you learn, because I mean, everyone, let's say, who worked in deep learning knows what a convolutional network is, but when you prepare a lecture on convolutional networks, you will go out and read the recent literature and put together all the recent architectures, look at them and play around with them. And that is something, I mean, you can do it without having to teach, but it's like an additional motivation to kind of like dive deeper.
It's a forcing function, the deadline.
Yeah. yeah.
But by the way, to our listeners out there, things have changed a lot from the early days of this deep learning renaissance, when maybe you didn't even have high-level libraries, and maybe I remember when I first started paying attention was around the time of Cafe, so it was still a bit hard. Now you have better libraries and model hubs even, right? So particularly in NLP. So I was just doing some NLP a few days ago, and I was just blown away by, man, there's so many embeddings now that I can use, and I don't have to do everything from scratch. So Sebastian, with that said, what is the state of deep learning for someone who's like a developer, someone who's not a data scientist, someone who's comfortable with Python? So what's the learning curve in terms of getting them to be kind of productive? I guess what's the title? ML engineer at this point. So what's the road to do learning enough deep learning so you can really contribute?
Yeah, that is a good point. I'm not like an engineer, let's say. Like I know these topics, but I'm not like someone who, let's say, is deep into the topics like deployment yet, at least not yet. But it's also one of the reasons why I'm currently at a startup company where I have colleagues who are very smart and specialized in that, and I'm learning these.
So take someone who's good at that, but then how do you teach them enough ML and deep learning?
Yeah, so I think one key is also understanding like why do you want to use deep learning, and instead of just, let's say,
what use case are you targeting?
Yeah, so what is the use case, and is the problem you are trying to solve even like a deep learning problem? So what I'm trying to say is maybe before, like, let's say deep learning is the goal. You want to use deep learning, let's say, for the sake of deep learning, but it is.
Let's divide it into two stages, right? So the first stage is so set aside this case where maybe it's mostly structured data. It's debatable whether it's deep learning. But let's say I'm a developer and I was tasked to work on images.
Mhm.
How easy is it these days for me to get going?
Also, oh, I think it is pretty straightforward, I would say. I mean, this is like a big claim, but nowadays we have libraries that are way easier to use than, let's say, Theano or Caffe back then. I think Caffe targeted an audience where you were not supposed to be coding, but more like using these configuration files. I was actually recently in one of my research projects looking at some Caffe models because I wanted to implement them as a reference, like a comparison to my method that I was developing. It is, I think it was harder to use Caffe than it is nowadays with, let's say, PyTorch. With PyTorch, for example, or even with Keras and TensorFlow, you can get very far because there are, first of all, lots of examples. So if you do an image classification, you take something like MNIST, for which you have a lot of examples, get that to work, and then you swap out just the data set, maybe the last layer with a number of classes, you maybe tune the learning rate and so forth, but you can get going very quickly. And then also, for example, in PyTorch, there are the Torch Vision models. So it's like where you can load even pre-trained models, models that have been pre-trained on ImageNet, and then you can fine-tune them or just train them again, but you don't have to write the whole neural network code. I mean, I think it's relatively easy to code like something, let's say a LeNet or AlexNet, like these traditional convolutional networks. But even like a ResNet 34, I think I have examples on my GitHub where I coded this from scratch a few years ago, but this is a lot of work. And it's not necessary because these are already provided in the model hub. So you load that and that's how you go about it. But then a good question is, okay, this is my model, but this is, you can train it on a GPU easily, but this is something I think that is also already outdated. So how I did my research was really tuning one model on one GPU, because it was the way I knew how to do it, and also due to, let's say, my computer, how it was set up. But I think nowadays, if you look at models, they are so large that this is not really feasible anymore. It would be very slow, basically, to do that type of work where you have one model per GPU. And nowadays, I think that is also where things like multi-GPU training paradigms become interesting, or
Ray.
Yeah, or mixed precision training. Yeah.
No, use something like Ray.io.
Yeah, for example, right. So for the distributed stuff, I mean, PyTorch Lightning company, like the open source framework, the company where I work at, we also specialize on making this easier. I actually saw there was like an example with Ray and PyTorch Lightning even.
I think there's some cooperation. Yeah. So one of the things that it seems like also has changed is, in certain domains, like I alluded to in NLP, you have these model hubs. So you can go and get started with some models from a model hub. So it seems like the focus of the tool builders has shifted a little bit from building models from scratch to helping people fine-tune models, right?
That is right, and I think, though, I think you still have to worry a little bit about practicality, though. I mean, there are different objectives. One is performance, let's say computational performance, and one is predictive performance. So I think with these model hubs you mentioned, they are very large, powerful models that you can fine-tune, but it is, I would say, still not trivial. It looks trivial in code, but for example, in my book, I was using the IMDb movie data set, 50,000 examples, as a data set to work with or to play with. And I solved this, or there was a classification task, a binary classification task, predicting whether someone liked the movie or not based on a review text. You can go about it with traditional methods like logistic regression and a back of words model. You can go about it with a recurrent neural network, or you can use one of these large language models from the model hub. And I did all three in that book. And just to tell you like the comparison, I think the Scikit-Learn version, the logistic regression classifier, took like 1 or 2 minutes to train. The recurrent neural network took like 5 minutes. Performance was, I think, slightly worse for the recurrent neural network because it needs usually a little bit more data than these 50,000 examples. Then for the model hub, I used a BERT model, BERT, the large language model. And actually, I couldn't even use that one because it was too large, so it didn't fit into memory. So I had to use something called DistillBERT, which is like a smaller version of that. So see, there is already the trade-off. I need a GPU, and I have to fit this into my GPU memory. So if I develop something, let's say for my cell phone, and I want to use that app offline without, let's say, internet connection, then how do I do that? I mean, it's maybe a big model that doesn't even fit into the in the memory and stuff. But then also one thing is about fine tuning. It sounds like it's super easy, and it is easy if you look at the commands. How you do that? It's like 5 lines of code or something. But it took, I think, half a day to fine tune the Dilbert model on the movie review data set. And I think it was just 3 training epochs. And RNN, for comparison, ran in 5 minutes, the training. 5 minutes versus like half a day. So it's still like a resource consideration. It is easy, I would say, to use these models, even like, I mean, code-wise, but even then, I mean, it's always a trade.
No, but I mean, what you're describing there, I think is fine, because basically, imagine you're a solution provider for NLP in some very specific domain, like finance, right? And so then what you would do there is you have some default model for tax classification. I don't know, I'm just making this up, like default, loan default, right? Tax classification. And then the user can fine tune it by labeling a few more very targeted data examples. And then you would take care of the rest in the backend. So I guess what I'm saying is that it seems like there's a gradual shift towards more, taking advantage of the domain expertise of the user, and taking advantage of the fact that we have a lot of models that are capable to solve many of these problems, right?
That is very true. I think these models are great because they kind of work already on general purpose classification tasks, and getting them to work is one thing. So you have this as like, let's say, people call that foundation, but it's like
that's a new term, right? The foundational models. Yeah.
I sometimes jokingly call it the F word in deep learning, but anyways, because people don't like this word, or some people don't. But let's say, we have these, that they work, and then you can fine tune them, and this gives a lot of power to the users, because they can, with a few data points, get going and get good results. But then let's say, it really depends still on the application, I would say. Let's say, was just thinking about it. Let's say my iPhone, when I'm driving, I use, let's say, Siri to get the directions. And sometimes the internet connection is not good enough, and it says, sorry, I can't process your query right now. And this is, I guess, because the natural language processing engine runs on some server, because it's maybe not small enough to fit on the phone.
The Android models are much more efficient.
And see, so there it would be a use case where maybe I want a smaller, more efficient model. Or you don't have to go with one or the other. You can even switch in terms of the context. No internet, use the small model on the phone. If you have internet, use the big language model, natural language processing that is on some server somewhere, right? So
this is that whole trend among researchers that they call data-centric AI, which is funny to me, because most people in industry have always been data-centric, right? So a lot of people in industry have always focused on data. But then for some reason now researchers are like, so this data-centric AI is a new research area, which is fine. They can come up with more tools to maybe help you learn with noisy data, or help you label your data more in a more scalable fashion and stuff like that. I just find it amusing that something that industry people have always considered more important, which is concentrating on data, is now a big deal.
Can I say something about that? I think I agree with you. I haven't been around in industry that long, so that I don't know the history. But I believe you that people always try to, let's say, modify the data to get better performance. I do think, on one hand, like you said, the data-centric AI term is maybe a buzzword, where to make it like deep learning, to rebrand it, to make it, let's say, more attractive.
Or no, it's also, honestly, it's a good rallying. It's a good way to rally people around. This is what you should focus on. It's a good thing that it's happened.
And I think there is some novelty in the case that before or traditionally, yeah, of course, we always try to optimize or modify, improve the data. I was actually, just before we met, I was reading this paper on label uncertainty and noisy labels. I just posted something on this about this on Twitter, but on a side note, but
is this Clean Lab? Clean Lab?
Huh? So this was one of my papers. Sorry, screen.
Oh, okay.
That was like a method where we it's like for virtual screening, but yeah, sorry, I lost the thread, but like the data-centric AI, I think the novelty here is really that we focus on, or the focus is really on developing tools for doing this more automatically, really, like instead of having humans. So I think that, like you said, it is a good rallying around this topic, and I find it very interesting. And I think the end game, or not end game, but the goal here is also to give more power to the users. So coming back to the model hub topic that you mentioned, that if we have more efficient, so because I think in many
users could be of many users of many stripes, right? So users could be just mechanical Turks, or they could be domain experts, right? So sometimes helping some of these data-centric tools requires access to experts to label data, right?
Yeah, and it is exactly. I think the challenge is also in many problems. So either you have machine learning people who, let's say, are not domain experts, so they are not very good at labeling things. But then you have domain experts who are not that, let's say, good at machine learning. They can label things. But overall, in real world problems, based on my collaborations or just talking to people, I think the challenge is really you have only a limited number of data. And so you want to really get the best out of it. And when I worked on computational biology problems, when people were developing methods for predicting whether, let's say, a molecule is active or not, or is docking to a protein or not, they were always trying to develop these general purpose solutions where this should work for all types of proteins, all types of contexts. And I think this is a reasonable approach to start with, because you get, like, you can benefit, the benefit is big if it works. A lot of people can use it very well. But one of the, I think, advantages or powers of machine learning is that we can customize it. Coming back to the model hub idea that you mentioned, where we fine-tune things. So in that case, you can actually have people in industry develop their special model. Like, it's not like some generic model, it's a special model, but for that special model, you really need the good quality data. And then, yeah, the data-centric AI becomes, I think, really interesting. I'm really excited.
So this is how I organize data-centric AI. So there's a class of tools, like you said, where these data-centric tools allow you to basically start maybe with labeling functions and then scale and label larger data sets, right? And then there's a class of tools that allow you to learn even if your labels are noisy. This is like, I guess this is like Clean Lab. I like Clean Lab, actually. And then...
Oh, I'm sorry, I misunderstood you before. I didn't. I thought, yes, Green Lamp was a project I worked on. I thought, yeah, Clean Lab. That is,
Clean Lab. Yeah. And then there's maybe, kind of active learning, data annotation kind of tools. And then there's a class of tools that I still bucket under data-centric AI, but have to do more explicitly with helping you improve data quality, right? And then, I don't know how you feel about this, Sebastian, but I'm also bucketing kind of this union of data exchanges, data markets, and then confidential computing, right? So if you have good tools for doing confidential computing, I don't know what that would be: federated learning, secure multi-party computation, homomorphic encryption, differential privacy, a union of all these tools. Then maybe you can start cooperating with other entities with data, right? So yeah, I kind of include everything related to data-centric AI, not just kind of the classic weak supervision
cleaning
kind of things.
Yeah. No, I think it's an interesting problem also to think about, like privacy, data security. This is like not my area of expertise, but it's a big issue.
But this must be something you've thought about because you work in biology, right?
Yeah, so I must say here, I worked a little bit on like privacy. So it was based on in a biometric context. It's also funny, when I joined the department, there are people in biometrics in our department, but a different type of biometrics. So there are two types of biometrics. One is like mathematical methods for biology, and one is like biometrical face recognition and fingerprints. So the term is used in two.
Oh.
But so my expertise is more like, or the areas I worked on was not the biology biometrics, but the face recognition biometrics, where we try to design systems where, let's say, an algorithm can't guess the gender from a face image to protect privacy, like preventing people using algorithms to automatically, let's say, do like surveys on gender if people didn't give permission. But coming back to that problem in biology, we luckily didn't have this sensitivity issue, because we were really working with problems that were not, let's say, sensitive. But I know what you mean. It could be a
genome or whatever, right? Yeah.
Yeah. So
or even yeah. Or even kind of some of the drug discovery trials, which you have to keep confidential patient data, right?
Yeah. So in our case, we worked on one project where it was about, let's say, a sea lamprey, an invasive species in the Great Lakes, which we wanted to, where we wanted to prevent like this invasive species from proliferating in the lakes. So there was no like sensitivity issue. But in one application here, we designed or found cancer inhibitor for colon cancer, and this was not based on patient data, though. It was based on, we had molecules and there were like some lab assays. In that sense, we didn't have to worry that much about, let's say, sensitive data, because it was really, the data set with the study was published. So in that case, we didn't have to, I mean, it was even like, what I'm trying to say is like, it was data sets that can be used by other people. So it was kind of like encouraged to share that. But yeah, and other applications, in medical applications with patient data, of course, this would be a big issue. I think Andrew Trask.
I know him. Open mind. Yeah.
Yeah, I know him a little bit from social media and his resources. He would be one person. I think he specializes really.
I'm actually. I just became an advisor to a very good startup in this space. That I guess by the time we aired this podcast, might have already come out of stealth, but I shouldn't mention their name until they do. But anyway, they're quite good. I mean, really. And I've looked at a lot of companies in the space. So earlier on the conversation, right? So you were alluding to the fact that, before you actually learn, spend time learning deep learning, maybe you should figure out if your problem actually fits into the deep learning framework. So let me ask you this. So where do you fall in when it comes to structured data? So does deep learning have a clear advantage there over, let's say, XGBoost, or in the case of time series, classic time series methods? So what's your sense of deep learning when you're in the purely structured data realm?
Yeah, a big question or topic.
It's hard to answer, but we're in a podcast.
I have a few thoughts. So first, of course, right now, gradient boosting, let's say XGBoost, LightGBM, and so forth, are really, people say these are the tools you need to use for structured data because they win the Kaggle competitions, which is to some extent true.
They're also maybe more efficient too, right? So.
Yeah, but also to some extent, based on my, let's say, experience, personal anecdotal experience, it's not always like the solution even to tabular data. So it depends really on the data set, also how big it is. It is, in my experience, very easy to overfit with XGBoost. So we have I was recently working on a project where we have only a few hundred data points, tabular data points, and I used k-fold cross-validation in that context, but even with XGBoost, because I tuned it so much, it was crazy, but I had like 100,000 hyperparameter tuning steps. It was overfitting to the k-folds, like it was memorizing which k-folds. So you can kind of prevent that by having repeated k-folds.
But still, the winner in your case is not deep learning.
Yeah, in that case, it was a random forest that actually performed very well. Yeah. But also, actually, surprisingly, a multi-layer perceptron performed very well. But coming back to that problem, like deep learning for tabular data,
or time series, right? So.
Yeah, so based on top of my head, like last year, there were at least, I think, 4 or 5 papers Forgot the names of the methods. One was called TabNet. There are some.
Oh yeah. I've had TabNet people on the podcast.
Oh yeah, for me, I tried.
I've used it. I've used it, and it's interesting, but it's obviously slower because it's doing a lot of computation, and also you don't quite. It's kind of a black box, right?
Yeah, and you have to be a little bit careful also with hyperparameter tuning and stuff. So personally, in my experience, it didn't work as well as other, let's say, traditional machine learning methods. Even like a multi-layer perceptron in my case was better. I have not extensively experimented with all the other methods, but following the articles, there's usually one article that comes out, proposes this new deep learning method for tabular data, and then 2 weeks later is this article saying, no, XGBoost is actually better or something. It's like this back and forth. And I think right now we are at that point, the inflection point, where I think you can get the deep learning methods to work as well as, let's say, XGBoost, maybe slightly better.
But it's not head and shoulders above, where you drop everything.
Yeah, right. And at the same time, like you said, it's exponentially more effort to do that. It's like I would say
whereas in computer vision and text, it's game over there, right? So
so right now, computer vision. But also, it depends on the data set, I think. If you have a very small data set, if you have a face recognition data set and you have 50 face images, maybe not a case for deep learning. Maybe you want to use facial recognition, key point extraction, and then you have like, I don't know,
SIF-hug
key points. And then,
SIF-hug. You just do feature engineering, right? It's a classic processing.
The manual feature engineering, right? And also, I think for interpretability, like because you can't really you can get great performance with deep. So take iris, for example, iris flowers, right? I mean, you can collect pictures of iris flowers and then apply a convolutional network, which would probably work well if you have 50,000 images. But if you only have 100 iris flowers, the manual feature engineering, like measuring the petal width and height and so forth, is probably a better bang for the buck, like doing these measurements. And then applying a classifier, you can get like, I don't know, like 99% accuracy compared to taking these pictures. So it's like always the trade-off. What does your data look like, right? So it is tricky, but
so like so at this point you're super busy, but whenever you have, I don't imagine you have much free time. So whenever you have free time, what new things are you exploring in this space? So what directions are you interested in? Is it more large language models, more multimodal models, more responsible AI? So what's on your plate of things to learn?
Yeah, so I have like two things, like I would say multiple plates even. One plate is really when I read or just newsletters and keep up with archive and stuff, I bookmark these interesting papers, and I usually pick like 3 or 4 papers each week that I read, and they are mixed. It's just like for keeping up in general. So I try to keep general, like
there's so many papers. There's so many.
Right. I was a moderator for Archive, the machine learning category in Archive, CSLG, and I was skimming through the papers almost every day. We wanted to see if they are categorized correctly each day when people make submissions. We have a model for that to predict the category, but it was not always accurate. Long story short, there were like 150 to 200 papers sometimes per day, and it is like overwhelming. So you can't read it all, but yeah. So one thing is like the fear of missing out. You have to kind of balance that. So I just collect interesting stuff, put it in on a text file, and then I pick out some of them. I realize I can't read it all, but just the most interesting ones. But what I currently are interested in is it's an old topic, but it's still model evaluation. So I try to like more general, like how do you evaluate models? I mean, there are different metrics. I was recently like getting more deeper into Matthew's correlation coefficient and these types of things, just metrics wise. There were like a series of papers that I was interested in. Then
which has big implications for MLOps, right? So because basically what metrics are you going to monitor, right? So right now, depends on the use case, depends on a lot of things, right? So
Yeah, right now I'm working on a paper benchmarking models for computational biology contexts with including graph neural networks and so forth. And there we have like these problems with also imbalanced data, how to sample the data if you have, because you have like these scaffolds and stuff. And this is a big problem, like what metric do you use? Because it's highly imbalanced and ROC curves are not really good at that. You can use precision recall curves, but then also more generally, what are the other metrics? Like Matthew's correlation coefficient is one of them. But that's one thing I'm interested in.
By the way, you just mentioned something that's really growing quite fast, graph neural networks, right?
Yeah. I'm actually very excited about that. I had like a chapter in my book about that on graph.
I mean, actual production use cases at companies. I mean, I think, and then the number of papers are growing quite fast, but I think the tools are still not there for industry people. So it has to be simpler for industry people, I think, right?
Yeah. So right now I'm using it in a computational biology context with molecules where the atoms of the molecules are the nodes and the covalent bonds are the edges.
What library?
And, yeah, right now, so there's PyTorch Geometric, which is more like a general purpose library, which it has. So personally, most of the work is done by one of my PhD students. So I think based on the feedback, most of the work is really getting the data into the right shape as input for these models. But recently I saw there is TorchDRUG, a new library that is specifically focused on graph neural networks for molecules. I think this might be easier. I haven't used it myself. I only saw that.
There's another one that I heard of, DGL. Deep Graph Library. Yeah.
I'm not sure if I maybe I've heard of it, but I'm not sure if I really.
So anyway, I interrupted you. So you have model evaluation. What are some other things you're excited about?
Also related to model evaluation, just last weekend I was working or diving again more deeply into confidence intervals, which I think is also an important topic.
Okay, you're in the right department for confidence intervals.
True. Yep. So so that is also one topic that always, let's say, comes up and is very interesting because right now. So one other topic I'm interested in research-wise is ordinal regression. Like how do we work or deal with labels where we have an order in the class table? So for example, most problems, benchmark problems in machine learning or deep learning are just
categories
that are not related, like iris flower species there's no ordering. You can't say Setosa is, let's say, more than Virginica or stuff like that. Same for, let's say, MNIST, where you have handwritten digits. You can't say a 7 is more than a 6. I mean, you can say that in terms of the number, but if you look at handwritings or image classification, a dog is not more than a cat and it's not more than a mouse. So in that case, we usually don't have these problems in benchmark data sets, but when you go to real world problems where you have let's say predicting the disease of a person, like moderate disease, severe disease, very severe disease, no disease. It's like an order.
Is this tumor in this medical image 1, 2, or 3, 4, 5 grade, right?
Yeah, right. So where you have, so you can tackle that with regression if you have a concrete number, like let's say centimeters or something. But often we can't really put our finger on like the comparison. I can't. So even Amazon reviews, it's like 1, 2, 3, 4, 5 stars. You can say, okay, it's always 1 star difference between the categories, but you can't really compare like the difference between 4 and 5 and 1 and 2. It's hard to put a finger on it. Like, is it like really the same distance? Or, I mean, there are even like for structural damage in a building or something, you want to predict, is this like a mild damage or severe damage, moderate damage? It's hard to say. Like, you can maybe as a human, you can label it as severe damage, but it's hard to like quantify in a number. It's not like a house price in dollars. It's more about the holistic thing. It's hard to say what's the exact difference. Or even for movies, if you like a movie, you really like a movie and you love a movie, it's sometimes hard to compare, like how much what's the difference between these two movies, basically?
There's a notion of order.
You're right, there's a notion of order, but you can't really quantify this difference. So and many problems in this real world setting or in real world settings are like that. And so I'm also working on.
So can't you use deep learning and create some embeddings and then just put some statistical model in the end?
Yeah, you could do that. You could do that. Actually, we have methods. So one of my focus areas of research is developing deep learning methods for exactly that. So we have like the statistical methods, the classic methods, but how do you transfer that to deep learning? And I mean, there are different approaches for that. We focused on extended binary classification framework. So we have like 2 methods for that, basically doing that, and it performs way better than regular classifiers.
So what you're talking about here is with your Wisconsin. You're wearing your Wisconsin hat right now. Yeah.
Right. Yeah. So there was so one paper we was like 2 years ago, and one we just submitted like last December. It's still under review, but the methods work incredibly well for image data, for text data. You can also apply it for tabular data. It's a general purpose method, a loss function. That so you modify the loss function and you modify the output layer, and that's it. It's like I coded it up like as a package, and if you want to use it in PyTorch, for example, you make 2 lines, you change 2 lines of code, and you get going, taking any classifier, anything like a ResNet 34 or something, or whatever you like, and just swap out the last layer and the loss function, and you have an ordinal regression model.
So Sebastian, since you're spending time in a startup and in industry, so how do you think this will impact how you teach courses at Madison?
Oh, so yeah. So right now, I like teaching a lot, but there are some things like when you're in academia, where, so personally, I'm, like we talked about before, I'm more like a technology person. I like my department, I like the university, but also just to keep current, let's say, with trends and experience. Like if I want to talk about, let's say, deep learning in real world settings, I kind of also need to experience this a little bit more, like in, let's say, in a real world setting.
So this will benefit students ultimately, right? Because basically this will inform how you present topics, the kinds of practical tools you'll introduce to the classroom, right?
Yeah, so right now my focus is really going like from research settings to more also like production settings, or not even that, but like using modern techniques for training and even at some point deploying neural networks. So my thing is usually I train the models, report the accuracy in a paper, and I'm done with that. But real world doesn't work like this.
No, it doesn't.
Yeah. And also even things like, even with Ray, like you mentioned, like multi-GPU training and these types of things, like how do you really, like what is the real workflow? What do people use?
It's funny you mentioned that, because basically I think that, when we think about academics, right, so being kind of outgunned, we always think in terms of, they don't have enough data, or they don't have enough compute to compete with people in industry. But actually a third factor is they don't have the systems programmers. Because basically you need engineers sometimes to set things up for you to actually just do the things at scale, right? So
right. So academia, I really like the work, but you are also really, you have students with whom you collaborate, research assistants, but ultimately you don't have, let's say, a team of engineers who help you, with everyday tasks. And also at the same time, we are lucky that we have university computing resources like clusters, but the way you use them is not very easy, and it is like very hard. Honestly, I got to.
They're like HPC MPI based.
Yeah, it is. We have actually a special one here at Wisconsin. It's called HTC Condor, which is essentially, it's like back then the folding at home, where every computer on campus is connected and it runs everywhere. But it is a little bit, I would say, not super user friendly. And that point, that's what we are also trying to solve at, let's say, the startup company Grid AI, where I'm currently at. Like, how do you make this really easy? Because, well, I'm as a deep learning researcher, there's only 24 hours.
It's easy, man. Just use Ray. Just use Ray.
Use Ray, for example. Right.
So what about things like fairness, interpretability, security and privacy? This whole responsible AI. Is this something you think about?
Yes, but it is not easy. Interpretability is a big topic. I think it also goes into fairness. I think in order to get, let's say, fairness, you have to also have interpretability, but I'm not an expert in that. But I think interpretability is, let's say, maybe the foundation, right? That you understand what the model is doing, and then from there you can look into the other things. It is, I'm not an expert on that. So there would be, let's say, Christoph Molnar, who wrote the Interpreter Machine Learning book. But it's something I deal with a lot because even in my computational biology work, so what you are trying to do is you're trying to find a molecule that has, let's say, some activity in a big data set. So you have millions of molecules, find something that is active. But you also want to understand why it's active. So you can find more of these molecules. And also, you can maybe then give it to a chemist, and if you understand what makes the molecule active, you can make modifications, chemical modifications. So in that case, I'm very interested in that. It is just a little bit hard to do that depending on what type of data you have. In a tabular data set, it's maybe almost easier than in a deep learning context. In a tabular data set, it comes back to what are your features, right? So I think, there are different methods, SHAP values, Lime, and so forth. But I think what is kind of also it's trivial but very useful is like counterfactual analysis. So where you say, if I change this feature a little bit, then
you should.
And then I get.
You're in a stats department. You should be thinking about causal learning and causal inference.
Yeah, that is another problem. I'm not, again, very, let's say, deeply involved in that. We have actually people in our department.
There's now some good open source libraries, by the way.
Yeah, I haven't honestly looked into these. I only know, I think the challenge is that.
Yeah, I just had a couple of Microsoft researchers who have an open source project, which I've been playing with, called Do-I, which does causal inference end to end, by the way, so speaking of libraries, so we talked about PyTorch, Lightning, and Ray. So what obscure library is in your toolbox that most people don't know about?
Maybe I would say, first of all, PyTorch Lightning. I think it's not super unpopular.
It's not obscure. Come on, man, that's not obscure.
Right. Okay. Let's say ML Extend, one of my own libraries, which is something where I put things in that are not implemented elsewhere. For example, let's say bootstrap methods for confidence intervals, or facial key point.
Bootstrap methods for confidence intervals are not implemented.
Not in Python, I think. Not
Python.
There are maybe some R libraries.
R definitely has it, right?
Yeah, but not like really Python. What else? Back then, simple things like making decision region plots.
By the way,
sequential feature selection.
In preparation for this podcast, I came across this interesting blog post you had with how I keep my projects organized. Do you remember this post?
It was probably 1 or 2 years ago.
Yeah. This is mostly, when you say projects, it seems like academic projects is what you mean, right?
I think yeah.
Because there's
everything
folders in there for grants, proposals, and things like that. Yeah.
There was a screenshot, but it is really, it's even our podcast here right now is a project in this folder. So everything basically, everything is I have learning projects. Each book I read is a project in there. Each research project, each let's say right now at my company, like things I create, everything that is like kind of like self-contained. Every talk, everything is a project, because I think it helps. For me at least, it helps me to keep track of things. But then also, it's very satisfying when you're done. You move it to the project archive folder, put a year and a month in front of it, and then at the end of the year you can also review what have you worked on this year.
So this is like ML flow for project management, huh?
Yeah, it's more manual, but yeah, it is kind of like it helps me to keep sane, basically, to have like a folder where I have at one glance every Sunday I go through that and see like, oh, I have to do something here, I have to do something there, just to know what is like urgent this week, or what things do I have going on. And one challenge, that's the biggest challenge, is how do you keep that list as small as possible so you can focus on few projects, because it's easy to grow that, and then while you are dragged into so many directions, it's like hard to keep up with things. What I don't like is doing too many things, because then you are very shallow in all these types of things. So I try to always focus on few things, but it is hard. So I usually always get, let's say, stressed.
So you don't. So what about calendars? You don't use calendars?
I use a calendar. I put actually everything. So my project folder there, it doesn't have any reminder things. I put important things always on my calendar. So I have for this podcast, things like that. But also if there's something important I want to do this day, so I put everything in the calendar, because that's like the main thing where I look, which is very useful if you are scheduling something. If you put also some of your main to-dos on there, because then you know, okay, this day maybe I shouldn't book a meeting because I have something I want to focus on. At the same time, yeah. So
in closing, so one of the things you mentioned as an area of focus is model evaluation. So is there going to be a Sebastian Raschka library, open source library for this?
Oh, I put a lot of stuff already into ML Extend, and one of the academic projects I had in mind when I started, what did I?
No, you have to, dude. You have to make it like a standalone library,
Exactly.
so people can
what did I call
people
it?
can just take it and use it, right? Instead of going into ML Extend.
Right, and I had actually a really cool name for that. I just didn't. It slipped my mind, but it had a cool name with AI in it. It was not evaluate, but it was something cool. I forgot. I have it written down though. But yeah, this is something on my list I wanted to always do at some point. And I also wanted to do it like that. That you can use a command line interface. That you only have to swap out the data set. That you don't have to learn, let's say, all the API usage. So it's just. But I never really got to this. It's one.
Yeah, I mean, I think it would be cool to have that.
Yeah. Yeah. This is one of the things. It's currently in the project hold list, but it actually I presented this when I did my faculty interview back then when I started at the University of Wisconsin. But yeah, one of the things on my list. First of all, there will be a blog post though next week or so. I was just reading another article. I have it here on my desk. It's called "Machine Learning: State of the Art with Uncertainties," where they referenced some of my stuff, and I wanted to just compile a list of methods in practice, let's say with code, that actually people can use to do model evaluation, not model evaluation, confidence intervals specifically. Because yeah, you can have a library for that, but honestly, most of the stuff is relatively straightforward. It's like 6-7 lines.
Yeah, most ML people don't think in terms of confidence intervals, for one, right?
Yeah. It is becoming more popular though. So it is something people I think should focus more on, because it is. I mean, with deep learning models, it is sometimes hard to tell, do you make progress or not? It's like run things multiple times with different random seeds to get different results.
Yeah. Definitely the Bayesian people are much more likely to think this way, right?
Mm-hmm.
Yeah.
But also, on the one hand, Bayesian methods are not super. I forgot the name of that. There was one really cool method, but they are not super easy to use either. And then they are only in R, and deep learning people, let's say, they don't look there, and it's really hard to get the adoption. I like what you said. I think what is really needed is a library,
a standalone. Yeah, a standalone eval lightning.
Mm-hmm.
I'm a bad name. I'm a bad namer.
I forgot what I called it. I have to look it up later, but I had a really cool name for that. But yeah, maybe I will just save it for a rainy weekend. And yep.
And with that, thank you, Sebastian. And once again, the title of the book is Machine Learning with PyTorch and Scikit-Learn. And I have a link to it in the episode notes. Thank you, Sebastian.
Yeah, man, that was a fun episode. I really enjoyed it. It was like a lot of interesting directions we took here. It was like totally unexpected, but super interesting. So I had a great time. So yeah, it was fun. And I really enjoyed this. It was fun.